2013 Level 3 Waves, Question 2. The Doppler effect. An ambulance with its siren on drives towards a stationary police officer. State the differences, if any, in the velocity and the wavelength excuse me, of the sound waves that are observed by the police officer compared to the ambulance. So the velocity of the sound waves has to be the same, because you're fixed by the density of the air and the speed of sound in air. But the wavelength, as it's approaching the police officer, is going to be shorter for the police officer, and that's my daughter getting up, so I'll pause this and finish it later. Okay, carrying on. B, the ambulance drives toward the police officer at a constant speed. That's crucial. Explain why the frequency heard by the police officer does not change as the ambulance approaches. So, just to set it up, here's our police officer. Looks more like a volcano with a puff of smoke at the front, but you know, because it's the labelled police officer. Anyway, ambulance, brick on wheels, coming towards it, constant speed. Just so that you've got this very clear in your mind about the setup of this, and a diagram is always helpful if you do struggle a little bit to understand the context. So the constant speed and why the frequency heard by the police officer does not change, so F is constant. And the answer is that the relative velocity between the source and the observer, so the source being the ambulance and the observer being the police officer, that relative velocity is constant. So any change in the wavelength due to heard by the police officer, heard by the any change in the wavelength heard by the police officer due to the bunching of wavefronts as they travel at the speed of sound, but as each successive wavefront is released by the ambulance, that bunching is constant due to the constant speed. So that's what they're getting at, and they're wanting you to explain how that process works. Now the next, or the last question is going to talk about accelerating, and as it accelerates, that means each successive crest is released a little bit closer to the next one than the previous one was. We'll get to that when we get to that, and I'll say basically the same thing. See, the ambulance passes close by the police officer and continues on past without changing speed. The frequency heard by the police officer changes from there to there. The speed of sound in air is 343 meters per second. Determine the speed of the ambulance. Okay, so our equation, we're trying to determine the speed of the ambulance. That's the velocity of the source. We've got the velocity of the wave given to us. We know the frequency adjusted. We don't know the initial frequency. So the adjusted frequency is either that or that, depending which way you choose to use the equation. And I'll better put up the equation. So the adjusted frequency is the original frequency times the velocity of the wave over the velocity of the wave plus the or minus the source, and it's plus or minus depending on whether it's coming towards or going away from. Just quickly cruising up here. Yep, we don't have any other values at all. Excuse me, so we can do a simultaneous equation, I would say, because we've got two unknowns here. Do we have two unknowns? We've got the velocity of source is what we're trying to find out. We know the adjusted frequency, simultaneous equation. So we're going to have to use F dash equals F VW over VW minus the source and plus the source up there. So we've got two forms of the equation, but one is plus and one is minus on the bottom. When you solve these simultaneously, I'll leave that entirely up to you. It's a mathematical skill. But the only crucial thing now is whether you use plus or minus for each of those two frequencies. So remember, as it's coming towards you, it's going to have a higher sound. It goes boom. As it goes away, it has a lower sound. So when it's coming towards you, it has a higher frequency. So for it to have a higher frequency that you hear, this frequency has to be multiplied by a number greater than 1. So whatever's in this this part has to be greater than 1. For that to happen, you have to be subtracting from the bottom, so that the velocity of the wave on the top, the numerator, the numerator is higher than the denominator. So it has to be subtracting. So this one here would be the one that you would use for when the frequency is higher. And then that's when it's coming towards you. When it's going away, 870 hertz, the lower frequency, means that you've dropped this, which means your frequency has to be multiplied by a number that is less than 1. Okay, so all of this has to be less than 1, which means that has to increase. You get the idea. Anyway, moving on. D, the driver of the ambulance then accelerates directly away from the police officer before coming to a sudden stop. So explain how the frequency of the sound heard by the police officer changes during this time. Let's just draw a very quick profile of the speed. Of the speed over time. That means, so the speed is increasing over time, and then it comes to a sudden stop. Okay, so there's no constant speed anymore. We were originally travelling at some sort of constant speed, but then we're not interested in that. We're only interested from the point where it accelerates and then comes to a sudden stop. And how the frequency of the sound heard by the police officer changes during this time. So first, what's going to happen as it accelerates away? Remember, you've got the so going away, it's going lower. So it's increasingly lower, if that makes sense. So the low shift is increasing as it accelerates because the velocity increases and those wavelengths that it's leaving behind, so as the source moves that way, it's leaving wavelengths further and further behind at each successive wavelength, so that the frequency will appear to be going lower and lower and lower as it accelerates. Okay, then it stops all of a sudden, boom, and it's going to restore to its original frequency. So it's going to go, if we were to do the whole profile as it comes towards, then goes past, then accelerates, and then stops, it's going to be something like, and back to that in the middle one. I don't know if you got that, but you can work that one through on your own. Definitely not a music teacher. But there you have it. I think that covers the main ideas. They might want a few more finer details of that, but that'll be all in the marking schedules, and I'm sure you're a diligent student if you're listening to this anyway. Have a good day. Actually, there's just one more video to come for this. This is only question 2 of 3.